Hi, welcome to the signal path. I just wanted to make a quick short video to show you guys something that I found in one of my dumpster diving sessions. This is a pretty interesting laser spectrum analyzer which comes in two modules. Now one of the reasons I just wanted to make a quick video is because I'm in the middle of a repair and the lab is an absolute mess. So if I go all the way here, you can see whatever is being repaired over there, and I'm going to keep that a secret. Won't tell you what it is until it's released, but it's a pretty expensive instrument that I bought, a pretty risky purchase. But you know, since I promised once the Patreon stuff starts, even though I haven't actually gotten anything from it yet, that I would buy some more expensive equipment, so I've done that. And on top of that, I updated my goals and things like that on Patreon. So take a look at it. I've added a few milestones, and I'm going to add some of the other perks and stuff that I would give away to my supporters. And thank you for those of you who've been doing that. And I'm also a lot more active on Twitter, posting little neat things here and there which you may enjoy. So you can go and check that out. But since I'm waiting for some parts to be delivered from DigiKey for my repair over there, so I thought, let's take a look at this. So this is interesting because it's very old, so it's essentially obsolete from the perspective of using it in a lab. Its resolution in terms of detecting optical signal is just very bad compared to what a modern, real optical spectrum analyzer would be. But for detecting roughly pretty close within a few nanometers of wavelength, it's still very good, and I think it's still functional. I haven't done extensive tests, but it does turn on, so that's one of the things I wanted to do on this video. So let me show you what it looks like on the front. So on the front, the controls are very basic. You have a cursor wavelength, which is a 4-digit 7-segment display, and that would be presumably to show you the wavelength, and this is to adjust, I guess, up and down. And there's 3 buttons here. There's a high gain mode, a hold, and a pre-trigger, which I'm not sure what the pre-trigger actually is. It moves the trigger point around, I guess, by a certain amount so that you could use the signals and give you some more time after the trigger. I presume that's what it is for. Now the gain here adjusts the detection gain, and this is essentially to be used with if the optical signal value is too strong or too weak, so you can adjust it so you can get a nice pulse. And the span is how much of the wavelength you're looking at, how much of it you're scanning. The reason this is useful is because if you don't know where your pulse is, then you want to look at a wide range. But once you've found it, you want to narrow the range so you get a bit more optical resolution. And there is really not much data available for this. I found a loose data sheet, but there's no schematic or real manual on how to use it. So I kind of figured it out based on some of the limited information that was available online. Now at the back of it is where the outputs actually are, because this number up here doesn't mean anything. This is not actually telling you what the wavelength is. This is what you set to. So this is not a readback. This is kind of a knob that you're adjusting. So at the back is where all the data basically comes out. This is how you can tell what the wavelength was. Aside from power, you have a marker, and that marker tells you the place where the wavelength basically rotates around. So without the marker, you don't know where you're scanning. So this is your reference point, so you can adjust with respect to that. The trigger, the trigger is also, well, let me rephrase that. The trigger is at the beginning of every cycle. The markers are individual points in the scan that tell you the discrete steps in the wavelength. So they're a little bit different from each other. We're not going to use the marker that much, but I'm going to use the trigger. This is my guess because it says 1 volt per division. Okay, maybe it has to do with, maybe they've quantized this at some level. Anyway, it's a pretty weird signal when you look at it on the oscilloscope. The signal itself, 1 volt per division, is the actual signal being detected by the optical. So this is where we'll tell you where the wavelength actually is going to be with respect to the trigger, which will tell you with respect to whatever is in the front set. So if you move the front wavelength, then the signal with respect to the trigger would move, and that's how you do the alignment. Now the optical head here is the signal that actually connects to the head where the optical processing is done. This thing has no optical components in it. It has no detectors. It's all analog and digital, and we'll take a look inside of it. But the laser spectrum analyzer module itself is where the optical input is, and right there you got an optical fiber optic connection right there, and at the back is where it rotates around and goes into there. Now this one, based on what I can tell, is an infrared detector, so it's made for infrared, most likely for optical communication systems. I wish what I had found was a visible light laser spectrum analyzer, because that's much more interesting, because I can do other visible light experiments with it. I have quite a few ways of measuring wavelengths in the infrared region already. I have a very good HP what do you call that? What do they call this? They call it a wavelength meter. That's right. And I've taken that apart and I've done a repair on it and so on, so you know quite well what's going on in it. And I explained exactly how that one works once we took it apart, and it's quite beautiful. This is different from that, quite different from that, the way this one works. So let's take a look inside of this one. And, geez, this was easy to open before. Now I can't do it anymore. There we go. So, as with almost every optical spectrum analyzer, at least the very precise ones, not the ones that are based on solid state, there are going to be moving parts in it. And this one is no exception. So it has a moving wheel. Let me zoom in here because I think it's interesting to take a close look at it. There we go. So it has a moving wheel, obviously, and this moving wheel is motorized. And you can see that there are divisions here, and this is how it knows when a full rotation happens. And if you look, somewhere on this wheel, the division is different, right here. And this is where it can tell where the reference plane is. That's how it knows the full rotation is. And the detector for that is on this side. There it is, right there. Very simple detector, just by interrupting the light between two LEDs. And a detector, pretty straightforward. And the light coming into the unit itself comes from right over here. That's where the fiber connection comes in. I'm sorry, over this side. And there's a slit over here, and that allows the light to go in this direction. And then it bounces against this mirror, and then is reflected on the surface of this grating mirror. Now I've explained in detail how grating mirrors work and why they work the way they do, and how they can use interference patterns in order to give you a diffraction of light and separate wavelengths. Very different from a prism operation. This is quite different than that, and go back and watch that video because it's quite interesting how these things actually work if you have never seen it. Which means that depending on the angle of this diffraction mirror with respect to the incident light that's coming in, the reflected light onto the other mirror is going to be a different wavelength, because once the light hits in here, it's going to spread. So depending on which angle I have set this, a different wavelength is going to hit this mirror and then bounce out and go through this little hole into a detector that's sitting right behind it. And you can see the wires of the detector come out. And this is really the main principal operation of this. So it's really straightforward. This thing's just going to spin like crazy, and every time it passes in front of the light, it's going to diffract the light. A different wavelength is going to hit that, and it's going to go there and get detected, and it's going to continue doing this. And because you know the location of this mirror, its angle, its precise angle with respect to that, you can compute based on the grating and how many lines there are per millimeters and so on this grating mirror, exactly what wavelength is being reflected into there. And if that wavelength is present, then it's going to generate a voltage on the detector, and that voltage is going to get routed out through some basic electronics and op-amps and so on back onto the control module, and that control module is going to say, hey, there is light in that wavelength. So you can imagine if there are multiple wavelengths entering here, you're going to get multiple detections. So you don't know which one is which. And this is why this is limited to only one wavelength at a time, unless you know exactly where the differences between them are, and then you can use that information. So pretty interesting and pretty simple design, and you can imagine because of its, the accuracy of this is not that great. So its resolution is not in the, tens of picometer, it's more in the few nanometer, and that's quite a big difference. And what about the main unit? Well, the main unit, as you would imagine, it would be pretty simple because it really has only the job of converting analog signals to digital, keep track of the reference where the grating mirror is, and that's about it. So it should be pretty interesting. Let me see. Oh, there's a wire there. There's an earth ground wire there. Let's put that over here. There we go. Sorry about the production values. They're not going to be great on this video, but I just wanted to produce something at least for you guys. There it is. Let's take a look. Obviously all through hole, nothing out of the ordinary here. Pretty interesting, straightforward design, nice and clean design. There are no mistakes in it, there are no bodges in it. Very interesting that they've used modules for their power supplies, because I guess they didn't want to go through the trouble of designing the power supplies. It wasn't probably worthwhile for them when they were designing this board to worry about that, and they just said, okay, we're gonna take something, you know, from another company, we know how it works, we're just gonna put it in and use it. And you would see this in test equipment often, because the manufacturing of test equipment doesn't care about these things. The profit margins are quite high because the number of these things sold is quite a bit smaller than consumer electronics, so they say, what the heck, let's put in whatever we can. And this Aztec one is also another DC-DC converter. This is an AC to DC converter, switching power supply obviously, and 110 volt coming in. Looks like 0 to 9 volts can come out, adjustable, neat. And there's a date on it, 15th of January of 1998, almost 3 days. It's pretty interesting, 3 days ago, almost 3 days ago, 19 years ago. That's pretty depressing how old we are, but anyway, this is quite an old unit. So having said that, you can see that there is an EEPROM, not an EEPROM, there's an EEPROM in here, but this is it has a window underneath this little sticker there, so that you can erase it with the UV. There you go, you can see it, there's a bit of the window there. I'm not going to completely take it off, and that's how you erase those things and reprogram them. A few processors, a neat colorful little switch over there. But that's it. I mean, there's a filter on the AC line coming in, there's a bridge rectifier over here, the LCD is over here, nice high quality potentiometers on these. And a very straightforward design, really nothing fancy. All of the firmware would have to do with keeping the data, you know, figuring out the alignment, making sure that everything's synchronized. This thing does have one feature that's interesting, is that if you press the hold button, it repeats the signal and repeats the signal you've been seeing, which means that it has to have a way of storing it and replaying it. So it does have some memory. It's not purely just passive spitting out information. So it's interesting from that regards. But anyway, enough talking about that. Let's close it up, turn it on, see it spit, and see if we can detect some infrared light. All right, let's go ahead and turn this bad boy on and see what happens. Here we go. And there it is. Look at it go. It's a Bobby Dazzler. You know, I actually have no idea what that is, but I'm assuming this is a Bobby Dazzler. So having said that, if you take a look, it boots up saying 800. I'm assuming that's 800 nanometer, and you can adjust that, go up and down. And even though the head connected to it, I think is infrared rated, this thing will go anywhere. You can set it to anything you want. It goes all the way down, even into the ultraviolet, all the way up deep into the infrared. So I'm not sure exactly how they know. I don't think they do. The unit probably doesn't know. But anyway, so having said that, everything else looks good and the knobs are nice, but obviously nothing happens when I do this right now because we're not looking at the signals, but these buttons all seem to work, which is great. So let's put it in the maximum span. Let's put it, I don't know, somewhere in the middle of the game and see what we can do with it. Now for a source, I'm going to be using this unit over here, which is an ILX Lightwave MPS 8033 precision fiber optic source. This one is a 1310 nanometer, is one of the optical communication bands, not the most common one, but it's one of the ones. It's good. It's not very deep into the infrared. It's kind of at the beginning of it for the purposes of communication, so that's a good thing to use. But what are we going to use to look at the actual signals coming out of it? Well, I thought we'd use something that we have never used in the lab before, and this is the Teledyne-LaCroix HDO 6104 MS. I've had this in the lab for some time, haven't had a chance to show you guys, and I've used it quite a bit, and it's a very, very interesting instrument. First of all, this is a 12-bit instrument, so that's why that HD 4096 comes from. 1 GHz bandwidth, 2.5 gigasample per second, uses Texas Instrument front ends, ADCs, plus the LaCroix's own amplifiers and signal processing and everything else to follow. But what is really cool about this is that it has one of the most extensive signal processing, triggering, math functions, and analysis on the waveforms that I have ever seen in anything. This is like a DSP's dream, because if you like manipulating signals and figuring out really complex computations on something right on the instrument, this is it. And it does an amazing job. There's just so much information. In fact, there's so much stuff they try to feed to you that the text is quite small, and they give you a little pen. It fits in here. It has its own little stylus, and you can then select and double tap stuff, and the menus come up, and just so much stuff. It really is quite extraordinary. If you can see that this was designed by a combination of people who know a lot about DSP, and that's not surprising because after all, Teledyne-LaCroix people were the people who invented the frequency stitching techniques for achieving very high bandwidth oscilloscopes. And I did a tour of Teledyne-LaCroix's factory. I showed you the 100 gigahertz oscilloscope teardown, which was really awesome. And this, you can see that the people who've done this are behind writing the firmware for these, because it's just ridiculous how much stuff this thing can do. So I'm going to do talk about this and show you some of this stuff later, because that's not what the intention of this video is. But pretty awesome instrument on its own. So anyway, let's go ahead and close this, because you don't want to have this open. Stray light obviously goes into the detector and throws things off. So I'm going to put this back without touching anything. There we go. And it sounds really bad, doesn't it? It sounds like it needs to be oiled. It just looks like it's not perhaps very well aligned. But anyway, it should be okay for our purposes. So let me get some cables, because it's not connected to anything, and hook it up to channel 1 and 2 and go from there. Alright, I've connected channel 1 and channel 2, and you can see that the way the scope starts up actually shows them separately instead of on top of each other. You can combine them, of course. But the other thing that's cool about this scope is that I know I shouldn't be talking so much about it, because that's not what this video is about, but even if you enable all 4 channels, the sampling rate doesn't drop, because it has a dedicated ADC per channel and 50 million points of memory per channel, which is crazy. I mean, this is again intended for doing a lot of computation right on the screen. So right now I can see that there is obviously some activity. Let me zoom into the screen, because this is one of those instruments that you need to look at the screen pretty close to see what I'm talking about. It's really bright here in the lab, making it a bit difficult. One of the things I wish this scope did have, though, is that I wish it didn't have a resistive touchscreen, because it has a resistive touchscreen. It works really well, but everyone's spoiled nowadays with the capacitive touchscreen. So anyway, so let's go ahead and select channel 2 here, and maybe reduce the time scale a bit so we can see. Oh, there is something. Let me 100 millivolt per division, maybe a little bit more. There we go, beginning to see something. There we go, nice. Oh, there you are. There are. This is trigger. This is a signal. So there's nothing coming out of the signal, but the trigger is generating all kind of weird process. It just grew, didn't it? Why did it just grow? What a strange thing this instrument is doing. You know, I think that the BNCs on the back of this laser source is not very good. Anyway, let's change that again. 1 volt per division. Not bad. And this is on 50 millivolt per division. Let's change that, make it 100 millivolt per division. So looking good. Now let me change the trigger. Under the setup menu, go over here, select the trigger source to be channel 2, and it has it. Just use a software assisted trigger stuff that it can do. It has all these triggers. I mean, it's crazy amount of information. And it may be overwhelming to someone who's never used it, but once you use it, the amount of capability it gives you and the flexibility it gives you is quite good. So let's change that over there and put it there. Now we have at least, so we're triggering on this rising edge of this particular pulse there. And I'm not sure why there are 2 pulses, maybe because of the rotation, the second rotation, and interesting that the timing is changing. Now if I change the span, can I do anything? You can see that, okay, by changing the span on the instrument, rotating the span knob, I can change the width of the first pulse. So this is minimum span, this is maximum span. Interesting. So yeah, at maximum span you get more compressed. Okay, so let's put it at minimum span. And let's see what happens if I... oh, of course I should turn the laser on. So there you go. Laser is now on. Let's see. Where's the laser? There it is. 0 dBm, and it's not on. Actually, there it is. Now it's on. Perfect. And of course we see nothing. That's because the wavelength on the instrument is set to 800 right now. So I don't expect to see anything. I mean, 800 nanometer is very far from 1310. So let's go up. 801, 802. Oh geez, I have to hold it. It goes, okay, now I'm at 870. Oh, I'm wasting your time. 940, 950, 60. Now I'm at 1000. 1050, I still see nothing at all. Oh, look at that. Pulses. But I'm at 1087. Okay. Let's change this a little bit. Actually, no, let me move it down. Let's put it here. How big are these pulses? These pulses are huge. There you go. I got the end of the pulse. So let's put it here. 600 millivolt down. Let me close that. There it is. So we can see the pulses. Ah, I get it. Look, the beginning of the trigger is not aligned with the pulse. You can see that the other one is moving. The end of one of the falling edge lined up with one of them, and the other one is somewhere in the middle of this. I think I'm beginning to understand. So this is the scan duration, and this is the pulse with respect to the beginning of the scan. So we're not at the right place. That makes sense. So let's increase that. It should move. There you go. It's moving as I change the wavelength on the instrument. Now we're at 1100. Now we're getting closer. 1200. There we go. Getting there. This is nice. It works. Oh, now we gotta zoom in a bit more. Ah, look at that. There's our pulse. And there's our trigger point. So now I can increase it. I'm at 1305, 1306, 1307, 8, 9. Look at that. It's not bad. You see, look, it moves around. So basically what I want is I want to line that up perfectly in the middle of that. That would tell me that I'm in the right place. Now it looks like that the signal is being saturated because, yeah, that's right. It's really, really saturated. Even at minimum gain, the top of this is square still. I think that's one quantization in wavelength. I don't think I can change that. So let's put it somewhere here. I'm just changing the gain and moving it this way. Moving it this way. This is the closest I can get. And look. Look. Check it out. 1308. But in reality, it should be 1310 because that laser source is very, very accurate. So if it is wrong, it's the instrument that I'm using that's wrong. It's not the laser source. So it's really close, but you know what? It had two calibration knobs at the end of it. At the back of the unit. So maybe I can toggle those and see if I can move this into the right place. That should be interesting. All right, let's give that a try. So in order to calibrate it, again, I don't have the instruction. I'm just going based on what I think is happening. So if I go over here, I'm gonna set this to 1310, which is the correct wavelength. So this is where it should be centered. Now if I look at the oscilloscope, you can see that it's not centered, right? It's not perfectly centered to where it should be. But the knobs at the back of the unit should allow me to adjust that. So let's go ahead and try that and see if I can get this to be in the right place. Let me see what this one does. Oh, there we go. No, this one doesn't seem to do anything. Let me try the other one. Ah, this one does work. Oh, look at this, it's great. That's pretty close, I would say, right? Yeah, this is good. Let me change the span. Oh, I see with it. I can even zoom in even more. You can see I have now even this is more. I wonder which one is actually zoomed in. So this would be a bigger span. This is a smaller span. There you go. So this is now dead on basically. So we just calibrated this thing. Well, it was pretty straightforward. Anyway, there it is, and you can see it works. Look at that. Pretty nice. Now I want to measure other things. What else can I measure? Alright, how about we measure a laser pointer? This is a green laser pointer, obviously. The wavelength of the green laser pointer is 532 nanometer. Now, having said that, obviously 532 nanometer is in the visible spectrum, you can see it. But because green laser pointers use wavelength translation, this actually puts out quite a bit of infrared, unwanted, undesired infrared light, which can be quite dangerous if it's not done properly. But anyway, which means that we do expect to see twice the wavelength coming out of this, also present, which we cannot see with the naked eye. So this should be able to detect it, and I'm just aligning it and shining it directly into the port. And in fact, if I look over here, I've already made the adjustment, and indeed we have signal there. And we see a couple of different lines, and it has to do with perhaps there are multiple wavelengths present, or maybe there are internal reflections because of the way this is lined up. I'm not sure, but either way, we can zoom in, and we can make some adjustments on the unit here, and bring this within there, and check it out. It seems to be pretty nice aligned, and if I go down here and we look here, 1067, and 1067 divided by 2 is very close to the 532 nanometer that is the wavelength of the green laser. So this is indeed working, and we can see for ourselves that we do have the extra wavelength of the infrared light present indeed within this spectrum of the green laser, which is undesired. So it all works. Anyway, this was supposed to be a short video. I think it's maybe close to half an hour. But anyway, I'm still gonna mark it as a short video because I'm just goofing around, playing around. But nonetheless, I hope you enjoyed this little video showing you something that perhaps maybe you haven't come across before, and also a little bit playing with the LaCroix scope there. And maybe if you're interested, we can do more stuff, but just wanted to give you a quick idea. So if you like it, give it a thumbs up. Obviously, any Patreon support is always appreciated, and even if no Patreon support, you don't want to support the website, it's totally fine. A comment is always nice to hear what you guys think. Feedback is always great as well. All right, until next time.